Now we're going to take important functions, exponential functions, e to power x and e to power minus x, and define new types of function that we call hyperbolic functions. For example, cosine hyperbolic or hyperbolic cosine is defined as e to the x plus e to power minus x divided by 2. And hyperbolic sine is defined as e to the x minus e to power minus x divided by 2. Basically, we can take hyperbolic sine and hyperbolic cosine, do the division, and define hyperbolic tangent and hyperbolic cotangent, and hyperbolic secant and hyperbolic cosecant. So why it is important? Because since we have a new function, we are interested in knowing what are the properties of these new types of functions. As you remember, we had trigonometric identities. For hyperbolic functions, we have hyperbolic identities. For example, if you take a hyperbolic cosine and raise it to the second power minus hyperbolic sine to the second, it's always equal to 1. 1 minus hyperbolic tangent to the second power is equal to hyperbolic secant squared. And the same for the rest of these important properties. You can compare these with what you learned in pre-calculus, and you learned about trigonometric identities. For a hyperbolic cosine at negative x is equal to hyperbolic cosine. And for a hyperbolic sine at negative x is equal to minus hyperbolic sine. So we can talk about symmetry of these types of functions as well. And we have more properties that we can use simplifying these types of functions. But what is important for us is to find the derivative of these functions. If you take the derivative of hyperbolic cosine, it's equal to hyperbolic sine. So as you can see, there is no negative sign here. You can plug the definition e to the x, e to power minus x here and actually verify this. For hyperbolic sine, you can take the derivative and it's equal to hyperbolic cosine. The hyperbolic tangent derivative is hyperbolic secant to the second power, and hyperbolic cotangent derivative is minus hyperbolic cosecant to the second power. The hyperbolic secant derivative is negative hyperbolic secant times hyperbolic tangent. And finally, the hyperbolic cosecant derivative is equal to negative hyperbolic cosecant times hyperbolic cotangent. And finally, a couple of proofs for you. So the derivative of hyperbolic cosecant cosine, which is defined as e to the x plus e to the power minus x divided by 2, you're basically taking the derivative of exponential function. The derivative of e to the x is e to the x plus the derivative of e to power minus x. Applying chain rule, you get minus e to power minus x divided by 2, which is basically the definition of hyperbolic sine. The same for derivative of hyperbolic sine. Hyperbolic sine is defined as e to the x minus e to power minus x divided by 2. When we are taking the derivative, we are taking the derivative of term by term expression here. The derivative of e to the x is e to the x, and minus the derivative of e to power minus x, minus and minus becomes positive e to power minus x, which is basically the definition of hyperbolic cosine. And finally, if you want to take the derivative of hyperbolic tangent, as you remember, is hyperbolic sine over hyperbolic cosine. So we're going to apply the quotient rule. The derivative of hyperbolic sine times hyperbolic cosine, which is hyperbolic cosine times hyperbolic cosine, minus the derivative of hyperbolic cosine, which is hyperbolic sine, times the numerator, which is hyperbolic sine. Basically, you have hyperbolic cosine to the second power minus hyperbolic sine to the second power, which we learned is equal to 1 divided by cosine hyperbolic to the second power, which is hyperbolic secant to the second